I will now introduce an important concept in quantum mechanics: observables and their mathematical representation provided by operators. So far, we've considered two physical properties of a quantum particle: position and momentum. As I've already mentioned, quantum mechanics is generally incapable of predicting the outcome of an individual measurement of either of these properties. However, it can predict the corresponding probability distributions, and, in particular, their means, namely the expectation values of the particle's position and momentum. We have already expressed the position and momentum expectation values in terms of the particle's wave function. Let's rewrite these expressions in a new, more suggestive way. For the position expectation value, we have the following. Since the squared modulus of any complex number is the product of the number and its complex conjugate, we can rewrite our expression like this. Here, the position variable x appears to be, so to speak, sandwiched between the wave function psi on the right and its complex conjugate psi star on the left. Then, for the momentum expectation value, we've previously obtained the following expression. We can also rearrange it to look structurally similar to the integral giving the expectation value of x. Here, we have an operator, namely minus I, h bar, times the derivative with respect to x, sandwiched between psi on the right, and psi star on the left. The operator is assumed to act on psi on its right, producing an ordinary function, which in our case equals minus I, h bar, times the derivative of psi with respect to x. In fact, what we've done for the particle's position and momentum can be generalized to other physically measurable properties of the system, commonly referred to as observables. In other words, x and p are examples of observables, the term used for physical quantities that can be measured. In general, the following relation holds for an observable O. Its expectation value is given by an integral over x, where the function under the integral is some operator sandwiched between psi on the right and psi star on the left. Here, the expectation value of the observable O is O mean, and the operator representing this observable is O hat. That is, for every observable O, there is a mathematical operator O hat representing the observable. In this expression, the operator O hat is assumed to act on the wave function psi positioned to the right of it. So, in quantum mechanics, there is a correspondence between physically measurable properties of the system, O, and mathematical operators, O hat, representing these properties. Let's write down a few notable examples in the form of a two-column table. In the left column, we'll put observables, along with their familiar classical mechanical symbols. In the right column, we'll put the corresponding quantum mechanical operators. Particle's position, x. The action of the corresponding operator, x hat, on a wave function psi amounts to simply multiplying psi by x. Particle's momentum, p. When the corresponding operator, p hat, acts on a wave function psi, it differentiates psi with respect to x and multiplies the result by minus I, h bar. Kinetic energy, T, which is equal to the square of momentum divided by twice the particle's mass. By analogy with the classical mechanical expression, the corresponding quantum mechanical operator, T hat, equals 1 over 2m, times p hat applied twice. The application of p hat twice to psi gives rise to the second derivative of psi with respect to x, multiplied by minus h bar squared. Total energy, H, defined as the sum of the kinetic and potential energies. The corresponding operator, h hat, called the Hamilton operator, or simply the Hamiltonian, is given by this expression. The Hamiltonian is of special significance in quantum mechanics. In fact, we have already encountered this operator. Indeed, if you review the early lessons in this course, you'll see that the right-hand side of the Schrödinger equation is nothing but h hat applied to psi. The concept of observables and operators is of central importance in quantum theory. Don't worry if you find this somewhat confusing at the moment. You will gradually become more comfortable with this concept as you progress through this course and work through various examples and exercises.